From my side, I'm security researcher at GData, and GData is sponsoring this event. We have an evening event this evening. We are all invited to share some drinks, eat some food, and have a discussion with the speaker. And also, if you want to get in touch with some antivirus researchers, you can also talk to us there. Yeah, have fun at the talk.
Okay, thanks. Okay, so is this working? Great. So yeah, thank you for the introduction. Today I would like to talk about cross-site scripting, or more specifically about DOM-based cross-site scripting, and the tool that we wrote to detect DOM-based cross-site scriptings in large numbers. So, but before we start with that, I would first again introduce myself. So my name is Sebastian Lekies. I'm a software engineer at Google, and at Google I'm working in the security test engineering team. That is a team that builds Google's internal web application security scanner. So we're building a scanner that focuses on detecting XSS. But the work I'm presenting here today is not coming from that. Before Google I worked at SAP, and I'm also a PhD student here at the university. And most of the content of this presentation stems from my PhD thesis, which is about client-side web application security. So if you want to contact me, there's my email address and also my Twitter handle. And now let's start. So let's look at the agenda first. So in the beginning, I would first like to have a brief cross-site scripting 101. Nicolas already sent me your XSS slides, so I will probably go over that a bit faster. After that, I will present how our tool works. So our tool basically consists of two components. It's a taint tracking engine that we built into Chrome, and it's an exploit generator that generates cross-site scripting exploits. And I will first show how we implemented the taint tracking engine and what the taint tracking engine is in general. And then I will talk about the results of an empirical study that we did with that engine. And we found a lot of suspicious data flows, so a data flow that is coming from some user input and ended up in some security sensitive function. And then we built an exploit generator to exploit these suspicious data flows, or at least we tried and succeeded in most of the cases. So I will show how this works and how many of these data flows in real websites we were able to exploit. And I will also show some exploits and how we generate things and so on. And in the end, I will give a summary, and then I will also give a demo and cover some future work, but without camera. So let's start with cross-site scripting. So I had the slides already, but somebody told me that only a few of you are visiting the lectures. So I wanted to first ask about your previous knowledge a bit. So I will soon show a few questions, and please raise your hand and just keep it up. And as soon as you cannot answer a question with yes anymore, put it down so that I know what you know about cross-site scripting, and then I can do the things a bit faster or a bit slower, depending on your previous knowledge. So who in this room knows what the same origin policy is and how it works? Okay, I think that's all of the people, or 99% of the people. Who knows what cross-site scripting is? Everybody? That's good. Who knows at least 3 different kinds of cross-site scripting? Still everybody? Who exploited the cross-site scripting by opening an alert window? Okay, that's great. You know everything. You can leave the room. And who really exploited an XSS? So not by only opening an alert window, but by really stealing a cookie, using the cookie, and doing something not illegal, but with it. Okay, some hands went down, but most of you know what it is. So I will go over the cross-site scripting section a bit faster to not give a boring talk. So actually, what is cross-site scripting? So cross-site scripting is a code injection problem, as you may all know. I have a very simple cross-site scripting on this slide. It's a reflected cross-site scripting. So we just have some server code that echoes back some get parameter from the URL. And this is obviously user controlled. And in the usual case, somebody would enter his name into this get parameter, and we would see a normal message, a greeting. But what an attacker could do, he could inject some HTML code. And basically what the server does, he processes this PHP script, prints out this HTML code, sends the HTML code to the client. The client has no clue that parts of this HTML code were coming actually from the user, so it just does what the HTML payload says, and this is opening an alert window, right? And you should all know this. So in general, in literature, we see that there are 3 different kinds, roughly, of cross-site scripting. I usually have 8 different categories in cross-site scripting, and I would like to briefly go over them and explain what we are looking at today and what we are not focusing on. So the first category of cross-site scripting was as cross-site scripting was initially discovered. So this is the reflected case and the persistent cross-site scripting type, where the cause of the cross-site scripting vulnerability lies in the server. So we have some vulnerable Java code, or we have some vulnerable PHP code running on the server and printing that out. And this was the first, in the first 5 years of cross-site scripting research, everybody thought that's it. That's the 2 main categories that we have. So then, in 2005, Amit Klein, this is the traditional XSS, yes. In 2005, Amit Klein published a paper about a new kind of cross-site scripting, and he called it the cross-site scripting of the third kind, and coined the term DOM-based cross-site scripting. And basically, we refer to everything that is caused by client-side code, so by JavaScript or VB script or Flash or anything that runs in the browser of a user and causes a cross-site scripting as DOM-based cross-site scripting. Here I distinguish between 2 different classes. So in the beginning, we only had the reflected cross-site scripting in that case. So some value gets immediately reflected back in the page. But nowadays, with a lot of HTML5 features, we also have stored cross-site scripting. So we have, for example, we have cookies where things can be stored. We have the HTML5 local storage API. We have IndexedDB. We have storage in Flash and in other plugins. So there are a lot of possibilities for also having persistent XSSs. And besides that, we also have a lot of XSSs that are caused by the infrastructure. So the first 4 categories, they are caused by application code. So there's an application running and we have code that a developer wrote, but we can also have XSS caused by other entities that are involved in rendering and showing web pages to the user. And the first thing is the client-side infrastructure. And an example for this category, for example, are universal cross-site scripting vulnerabilities that are occurring in browsers. So it's the browser's fault, not the application's fault. The second category that we have is the server-side infrastructure that may cause cross-site scriptings. So for example, in a few years ago, we had a cross-site scripting due to an Apache error message. Apache was showing a 404 page and said page index.html was not found. And if you search for something that contained a cross-site scripting payload, it would show, well, this cross-site scripting payload was not found, and you had an XSS. So it was the server and not the application running on the server. And then we have the 7th category, and this is caused by the network. And for example, in the US, there are a lot of hotel chains, and also some airlines are doing that. They are injecting advertisements into pages that people visit over their free Wi-Fi. So they offer free Wi-Fi, but when you visit a page, you see additional advertisements that wouldn't be there normally. I consider this a cross-site scripting attack because it clearly injects code into the application that is not supposed to run in the application. And if the application runs over HTTP, there's nothing the application can do against these kinds of attacks. And then we have an 8th category, and the 8th category is caused by the user. So this is basically self-XSS. So for example, if you go to Facebook and open your browser console, you will see a message. It's a big stop sign. It says, do not paste anything here, because people are usually forced into pasting something into the browser console, or they are talked into opening a JavaScript URL in the browser, which causes JavaScript code to execute in the origin of a page. And besides these 8 categories, we also have a lot of different combinations of all those categories. So for example, we can have a cross-site scripting that spans the server, so where you store something in the database, then this thing will be transferred back to the client, and in the client we have an API that actually makes a cross-site scripting out of it. So it spans server and client. So there's a lot more than these 8. But I think that's the basic categories that we should have. Okay, so as I said, the first 4 are application specific. They are caused by wrong code within the application, and the others are application independent. Nothing you can do from a developer point of view to prevent that. And today I would like to focus on the application-specific part and not on the application-independent one. So we are looking for errors that the developers do when creating applications. And I have another categorization for the same thing, so just some example, and I will go quickly over them because you all know what cross-site scripting is. So we already saw the reflected cross-site scripting where we just echo a name on the server side, and here we see it's PHP code running. Then on the server side, we also have persistent cross-site scripting. What you can see here is, in the first line, we just execute some SQL statement. We use some user-provided data in that SQL statement, store it in the database, and at a later point in time, we are selecting exactly that same data again and printing it out to the user. So it's exactly the same, but stored. The same we have on the client side. So here we have a JavaScript code, and here you can see the difference. This is server-side code, this is client-side code. And we see just this JavaScript code. The JavaScript code reads something from the URL and just prints out a greeting via document write, which is again a cross-site scripting. And I think probably most of you have not seen this one. This is stored client-side cross-site scripting, and we see them a lot. So they are happening a lot and people are not aware of them, so I have it in my presentation. So what is happening here is we are again reading something, a message, and the message is coming from user input, from location hash, and we are storing that, that message in the local storage. Is everybody aware what the local storage is? Yes? No? Some are nodding, so I think you are. So at a later point in time, we are reading from the local storage again. This can happen in a totally different page, not the one that wrote the payload into the local storage. And we can have a cross-site scripting when this is written to the DOM. Okay, so I will briefly also talk about the exploitation because this is mostly missing in most of the lectures. So they're just showing a vulnerability but not showing how to exploit it. But I think you all exploited cross-site scripting, so I will quickly go over it. So imagine you have Gmail and you have an XSS in Gmail. What would you do about it? Of course, you would show some cat pictures. And beside the cat picture, you would embed an iframe that you would make invisible and just insert the vulnerable page and also insert the payload. And in this way, you would send this page to somebody else. Somebody else would look at the kitten pic, would not see the frame that is executing in Gmail and executing a payload in Gmail. And hence, this kittenpics.org would be able to execute JavaScript and read your mails or send mails in your name and so on. The same we have for persistent cross-site scripting. So in a persistent cross-site scripting attack, you usually have something that stores user-provided data. Here, this is a very simple guest book. So we just enter a cross-site scripting payload into a guest book. And afterwards, we are storing that post by posting it to the guest book. It will be stored. And later on, users will visit this page and see your guest book post containing the cross-site scripting payload, and the payload would execute. So let's talk about the effects of a successful attack. So usually here we have an example with the website example.org. So in this website, we have legitimate HTML and legitimate JavaScript code that provides anything that you want to do, and you also have cookies in that page. And these things can be accessed via JavaScript. So JavaScript can alter the HTML, it can read properties from it, it can write new properties to the HTML, it can create new elements in the page, and so on. And the JavaScript can also access the cookies. So now let's imagine there's a cross-site scripting on this page. What would happen? So we would have an attacker from the outside, and he's somehow able to inject JavaScript code via the XSS. And this JavaScript code basically runs with the very same privileges as the legitimate JavaScript code. So this JavaScript can alter the HTML, it can read all the values that are in the HTML, it can alter the running JavaScript in the page, and it can access the cookies. So basically we can do everything that legitimate HTML does. And I will show some examples for that. So this is one example. It's very old. It's from 2006, I think. And there was a cross-site scripting in Bundesregierung.de. And what the attacker just did, he just inserted a fake message into this page. And what he did, he said, Chancellor Merkel will resign, and for some shady reasons, she doesn't want to deal with all those guys anymore and so on. So this seems to be very funny, but it's actually very severe, because you could also imagine there could also be a password dialog asking the user for providing a password. Or there was another case of a biotech company that was hacked. I'm not sure if it was cross-site scripting, but they hacked this site and they printed a message onto the start page saying, oh, we were acquired by a bigger company. This led the stock price to skyrocket by 50%. So if you have had some stock options for this company, you're probably rich. So I think if you have a persistent cross-site scripting and you are able to paste fake messages, this is a bad thing, right? Then here's a second example. So this is a news entry from last year. And the news entry is writing about the Ubuntu forums got hacked. So and in this hack, you can see it in the headline, 1.8 million user accounts were stolen, including the passwords. So what happened there is, you can see it, the attacker used a method called known as cross-site scripting, or XSS. And yeah, you can also see they stole the salted hashed passwords of 1.8 million users. And what happened there is that an attacker gained moderator rights in the Ubuntu forums, and a moderator is allowed to post HTML. So what the moderator did, or the attacker, he injected a payload and he wrote some messages to the administrator saying, oh, I have this new post, please have a look at this post. So the administrators went to this post, the cross-site scripting payload executed, they stole the cookies from the administrator, and then they had full administrator access to the forum and just downloaded the database, having all the user accounts. So to summarize this, if you have a cross-site scripting in a page, you can basically do two things. You can alter the web content, you can show messages on the page, you can show password forms to make the user enter his password, or you can also access the information that is in the page. So if there's private information, you can access it. And you can also conduct session hijacking attacks. And you can either do that by stealing the cookie and misusing the cookie, or you can trigger malicious actions directly, just by having some JavaScript code that does some requests or posts something on behalf of the person visiting. And to summarize this, with the cross-site scripting, you can impersonate the user towards the server. So you can use the cookies to say, hey, I'm the user, do what I want. And you can impersonate the server towards the user. You can tell, you can show any content, and the user will believe that this is legitimate content from the page. Okay, are there any questions regarding cross-site scripting? So I did this very quick because I think you all know that. Otherwise, I would now go over to talk about our tool. So basically, when we look at cross-site scripting, we see a lot of literature about reflected and persistent cross-site scripting, but there's almost no literature about DOM-based cross-site scripting. So we thought we should change that. And we wanted to write a detection tool for DOM-based cross-site scripting, because DOM-based cross-site scripting is quite new and quite unresearched, and also very complex sometimes to find manually. And to do this, I first want to show a motivating example. So maybe I can show this example here. So here's a cross-site scripting in there. I guess you all see it. So we have a variable here, and the variable is called URL. And this variable is filled from user input from location href, which is the URL. And then we have some other parameters. And then here in this line, we have some code that is constructed. So this is code from a real website, but it's a bit simplified. So what this website is doing, it inserts a beacon image. So usually websites do that to track users, or advertisers do that by inserting a small image pointing to the own domain and then providing some meta information so that they can see how you interact with the website. And in this case, this URL parameter is coming from user input. So this goes into this code variable here. And in the end, we are writing this code to the DOM. So it's a pretty simple XSS. We just need to break out of this parameter, and then we can insert script tags and execute JavaScript and do all the evil things. So in this case, I would first like to talk about terms that we use when in the next slide. So the first thing that we saw here is the source. A source is something where user input could be coming from. So all the DOM properties where user inputs, where things from the URL can come in, where attackers could control data. And then in the process of this cross-site scripting, we have some propagation of the data coming from this source. So we see that here is a string concatenation. So in the beginning, we are creating or internally in the browser, this would create a string. The string would go in here, and here we would create a new string because of the string concatenation. And then we would create another string from the string where the data went in, because we have another concatenation here. And then we would write this to an evil function. And this evil function we call a sink. And these names are coming from information flow research. So a source is something where things is coming from and it's flowing towards the sink. And you can also think of a kitchen sink where things are flowing in. So let's think about how we could detect these cross-site scripting vulnerabilities. So we want to write a detection tool. So the first thing how we could detect this is to do this manually. We could like read the code and then spot there's like data from a source going into this code parameter, and then this thing ends up in an evil function. But manually assessing these things has a lot of downsides. So for example, this was a very easy example, but usually JavaScript is very complex and you cannot easily manually assess it. Especially if you are not the code owner, then it's probably minified and sometimes also obfuscated. So it's really hard to analyze. And the second big reason is it does not scale. If you think about big companies producing hundreds of lines of or millions of lines of codes per day, you cannot assess them manually. So let's do it automatically. And if we do something automatically, in security we almost always have two choices. We can do it statically, so we could write a tool that parses the code, tries to understand how the code works, and tries to find out where the vulnerabilities are. But static analysis for JavaScript is very brittle because it's an open research problem. We don't have any good static analysis tool, and I think this is a pretty interesting PhD topic. So if you plan to do a PhD, this might be your topic. And if you use static analysis tools today, you will see that if you throw a jQuery into a static analysis tool, it will crash, or it will simply not be able to understand what you're talking about. And there are lots of other reasons why this is not working nowadays, and I think it would require another talk to talk about that. So I'll skip this and come to the next analysis technique that you can use. And this is dynamic analysis. And in dynamic analysis, it's basically executing a piece of code, trying different inputs, and analyzing it at runtime. And here we have, again, a few different options. And one that I think is pretty obvious is fuzzing. And here I call fuzzing, it's also known as blindly inserting payloads everywhere and just pasting alert once into all the get parameters and see whether a payload triggers. And fuzzing is good because it finds the low-hanging fruits, and you will quickly be able to write a tool in a few lines of code that finds XSSs. But fuzzing fails at complex vulnerabilities. If you have a very complex code and you just blindly paste payloads into an application, you will not find those complex vulnerabilities. So we decided to go for taint tracking. And taint tracking is a technique. I have a definition here. Taint tracking is the process of tracking a piece of data through a running program, basically, when we talk about dynamic analysis. So what we are trying to do is what we did manually before. So we saw there's this location href call, this goes into a variable, then we follow with our eyes, okay, this is going to string concatenation, and then it ends up in a security sensitive function. And this is exactly what we are trying to automate. So let me quickly explain. We have the example from before. In this case, we have this call to location href. And internally in the browser, this creates a string. And what we are doing in our tool is we attach a piece of information to this string. And we are trying to deliver this piece of information to all the places where the string was used. So at first, we are attaching it to the URL parameter because it's coming from location href. Then we see this propagation down here, and this leads this URL parameter to end up in a new string that is called code. So we are also attaching this piece of information to the code parameter, and then we see the code parameter is again used here and is concatenated with a new string. So we also attach this information here, And finally, the code parameter is used in an eval function. And by using that piece of information, we can determine that this was actually coming from user input, or that there was some value that the user was able to control. And if we find that it's a very suspicious thing, right, then we can look into it and exploit it. So this is how we do it from a high level point of view. And here's how we do it like on a more technical basis. And if you have any questions, feel free to ask at any time, right? So what we are doing is, here's another example. So we have a variable x, and this variable reads some user input. So this creates a string object internally, and this is the string object. And in the string object, in a JavaScript engine, usually you have 1 byte per character. So we have 4 bytes having this string that was contained in location hash. And for every byte in our string, we attach an additional byte. And in this additional byte, we store where the byte was coming from. So if the byte was not coming from user input, we just have a 0 in this 1 byte. If a byte was coming from user input, we have a numerical identifier of the source where it was coming from. So we have about 14 different sources. So we have 14 different numerical identifiers to identify where this byte is coming from. And then these strings get processed. So for example, here we see x gets into the escape function. And we are propagating this information, right? So this is the first call in our program. And in the second call, we escape it. And escaping might lead to a transformation of the string or the creation of a new string. So here we have see like a quote in the string. And this quote through the escape function turns out to be %27 in URL encoding. So we also transform our byte or our taint information behind there. So every byte in the string gets a new byte, and we use another numerical identifier to mark that actually this was escaped. So that we went through some function that did some transformation on it, so that we still know it. And here you can see the structure of a byte. So in total, we have 14 different sources where user input can come from in the browser. And well, to represent 14 numerical values, we exactly need 4 bits. And so this is a byte. It has 8 bits. And we use 4 bits for the numerical value. So we have 3 bits left. And we use these 3 bits to store encoding functions. So we have 3 different encoding functions that we have in the browser: escape, encode UI, and encode UI component. And we use 1 bit to store whether we ever flew through such a function, because sometimes this gives indication if a flow is exploitable or not. Okay, so in order to implement this into Chrome, so we implemented this into Chromium, in the open source version of Chrome. We patched basically the string types, we patched all the propagation functions, and we had to do this in the JavaScript engine in Chrome, and we also had to do it in the in WebKit, or nowadays it's called Blinked, in the rendering engine, because Chrome internally has 7 or 8 string types, so we had to patch all of them and have all the conversions between the types. And we did that, and the resulting thing was this. So we have a patched WebKit, and we have a patched JavaScript engine, which is called V8. And whenever a security-sensitive function is called, async, we check that piece of information that we attach to the string and check whether this was coming from user input. And when this is the case, we have a reporting module that sits here, and it will report the flow to an extension that we control. So we create the browser extension, and this browser extension basically collects all the data. And with this, we did an empirical study. So we mounted this to a crawling infrastructure so that we are able to do it on a large scale. And we scaled the Alexa top 5,000 websites with it. So with roughly 6 machines. And well, this is what we found. So we crawled the Alexa top 5,000 websites, and we followed all the links on the page. Nothing else, just the anchor tags. And with that, we found about 500,000 URLs that we visited with our patched Chrome and the extension and the crawler. And in total, we found roughly on average 8.6 frames on each website. So we analyzed about 4 million documents with our engine. And in these 4 million documents, we found 24 million suspicious data flows. So it's about 24 million flows that were coming from user input and ending up in a suspicious function. And this is pretty a lot, and we were surprised. We thought, oh, well, maybe we find a few and we can have a look at it manually and try to assess whether we found XSSs. But then we were like, whoa, 24 million, how would we do that? So we need some means of validation. So we need some kind of thing that tells us this is vulnerable and this is not a vulnerable flow. And the problem is that such a flow is not always vulnerable. And there are many reasons why such a thing is not vulnerable. So the first reason, I have an example here, is that there could be a validation in place. So here we see there's a call to document write, and the thing is coming from user input. But before actually doing that, the website checks whether this user input only contains alphanumeric characters. So when we first crawl the website, we see a flow because document write would be called with a non-malicious payload. But if you throw an exploit into that location, we would not see the flow anymore. So this is not an exploitable flow. Another reason is that also the server could do strange things. So for example, you could have a parameter, and when you change the parameter from a certain value, it's a bit simplified, then you might not deliver the script that has the vulnerability. So for example, here we see only if this ID value is 1, we deliver a vulnerable script, and the vulnerable script would use this ID parameter in the document write. So we would, in the first place, we would detect this, and then we would see, whoa, okay, we could tamper with the ID parameter, and as soon as we tamper with the ID parameter, the script is gone, and it's not vulnerable. So flow is not necessarily vulnerable. So we need some means of like generating or validating things. And well, when we did this, we saw as well, what is the best validation for vulnerability? Yeah, we should have an exploit for this thing. So we can exploit a flow and open alert window, then we are able, then the flow is clearly vulnerable. So we thought, well, we need something that exploits a thing. So we need an exploit generator. And in order to write an exploit generator, we first need to understand how do exploits look like. So let's talk about how cross-site scripting exploits look like. And the first thing that you will see when you write a lot of cross-site scripting exploits is that cross-site scripting exploits are context sensitive. So it depends on the context that you're injecting in, on which kind of payload you need to create. And I will give a few examples to clarify this. So the first context that you can inject in is obviously the HTML context. So in this example, we have a cross-site scripting vulnerability here. We have a document write, and we write a user input that is coming from location hash. And document write turns a string into JavaScript. So what you need is you need to create a JavaScript payload. Sorry, that was wrong. Document write turns a string into HTML code. So when you inject into document write, you need to create a payload that contains HTML. And we see this here. So here we have the injection point is inside an attribute. And to exploit this, you first need to break out of this attribute. You need to break out of the image tag, and then you are in a place where you can execute a script. Then you would open a script tag and have your payload and everything else. The next context that you could inject into is the JavaScript context. So for example, this is the case for the eval function. So here we see a cross-site scripting where we call eval, and we declare a variable that contains some kind of user input that comes from the URL. And in this case, our exploit needs to reassemble valid JavaScript code. So we would need to break out of the JavaScript variable. We would need to enter this JavaScript statement, and then we could again have our payload with alert 1. And the same is true for URLs. So sometimes you have injection points into weird places. So for example, here this creates an iframe element, and then it assigns to the iframe element source attribute a location hash, so again a user input. And if you have this case, you can inject a URL payload. So in this case, we inject a JavaScript payload, and the JavaScript URL would allow us to execute our payload again. So we need three generators for all the different contexts, basically. But if we step a step back and look at payloads, we see that there is like some common structure in such a payload. So the first thing we see when we compare all these different payloads is, well, in the middle we always have an arbitrary piece of JavaScript, and this is what we want to execute. And this is just a payload, and this we want to choose freely, right? As an attacker, we want to do some evil things here. And then we see two pieces in front of the payload and after the payload. And the thing in front of the payload we call a breakout sequence. So because usually your injection point is inside something where you cannot immediately execute a piece of JavaScript, right? You're in an attribute of an HTML tag. You cannot execute JavaScript there. You first need to break out into a context that allows you to execute JavaScript. And then we have the third part, and we call this a comment sequence. So sometimes, for example, if we are in a JavaScript context, we need to create valid JavaScript. And usually behind the injection point, you have a lot of values that would make your payload syntactically incorrect. So you sometimes need to get rid of the trailing content. And usually what you do, you just inject a comment sign that like says ignore everything that follows this thing. So, and if we look at the context sensitivity, we see that, well, the payload is not context sensitive at all. It doesn't depend whether we inject into JavaScript or into HTML or into URLs. We always have a JavaScript payload. If we look at the comment sequence, we see, well, it's not too difficult. If we are in a JavaScript context, we just use a comment sign, and in HTML, we use whatever we want. Here it's just a text area, and we need to close the script tag to make it syntactically correct. So these two are pretty easy to generate automatically. The only thing that is left is these breakout sequences. They are pretty hard, and you need to somehow think about how to automatically do this. And so what I would like to do now is I would like to talk about the HTML, how to generate exploits for HTML, and how to generate exploits for JavaScript. And in the end, I will also show the exploit generator and how it works on real websites. It is fun, I think. So let's talk about HTML. So what I did when creating this thing, I read the HTML specification, and the specification says you have exactly 3 places where you can end up if you have anything in HTML. So if you have any character in an HTML document, it can just show up in 3 places. And the first place is it can show up inside a tag node. And a tag node is anything that starts with an less than and ends with another angle bracket. And so if we are in a tag, an XSS payload is pretty easy to generate. So we only need to check, are we in an attribute? And if yes, we need to have the delimiter of the attribute in our payload as a first character sign. Then we are in the tag itself, so we need to break out of the tag to insert our script tag. So we need to close this tag by a closing angle bracket. And sometimes we also need to close the tag itself. So for example, if we inject it into an iframe and we close the iframe tag, we're in between the opening iframe and the closing iframe tag. And things between those tags will not be rendered as long as your browser supports iframes. So you also want to close this iframe tag to insert your script tag behind the iframe. The second place where characters can show up is inside text node. So you are not inside a tag, but you are in between a tag or just somewhere outside a tag. Well, this is pretty easy. If we are outside a tag, we can simply inject our payload directly. But sometimes we might also be inside an iframe tag or inside some other tag that does not render its contents. So we also need to have the closing tag for the previous tag that we are in. So when we are checking this, we're always just looking at this tag and just closing the tag that is in front of the tainted injection point. And the third place where you can be if you inject into HTML is you can be in an HTML comment. So a comment starts with this character sequence and ends with this character sequence. And again, this is very simple. If you want to create an exploit, you first break out of the comment, because in the comment you can basically do nothing. And sometimes the comment is also again in an iframe tag, so you need to add closing tags to this. And this is pretty simple. And here is an example. So here we have a cross-site scripting vulnerability. And this vulnerability, we have an injection point in an attribute inside a tag. And so what we do is we run our taint engine, and the taint engine will detect this because we have like the evil sync that is executing. And then what we get is the complete string that the function executed. So this is like at runtime, if we with this URL location hash would point to foobar, and so this is the string that ends up being executed in this document, right? And our taint engine would exactly tell us what is the user input. So it would show, oh, this part of this string that you got is the user input. So what we do is we parse this string, and then we just identify where are we in these 3 different locations that we can be. So this time we are inside a tag, inside an attribute. So to generate the payload, we just use break out of the attribute, then we break out of the tag, we close the script tag, then we just append our arbitrary payload that we want to execute in the page, any evil code, and then we just append a text area to get rid of everything that is else in the page. And we have an exploit. So this is an exploit to execute this thing. And this always works. So if you have a document write, this is pretty reliable. So let's now look at the JavaScript context. So here's another example for the JavaScript context. In this case, the web page constructs code from strings. So here it constructs a function, this is named test. And in test, we have a variable, and the variable is filled with user input. And then the function does something with this user input. And this is just a string, hence the web page throws this into eval and executes this. So and again, we have a cross-site scripting vulnerability in there. And when we have such a cross-site scripting vulnerability, we have 2 choices on how to exploit this. So the first way is we are inside a variable declaration. So we could just break out of the variable declaration. We could end the variable declaration with an semicolon, and then we could just insert our payload because we are in a JavaScript context where we can execute arbitrary functions. And then we need some code that like makes the rest of the function syntactically correct. If not, we will break the parsing and this will never execute. The other possibility is we could break out of this variable declaration, end the variable declaration, and immediately break out of this function test, because we can just insert a parenthesis, and then we can, after the function, insert the alert. And if you look at these 2 different possibilities, we see that this has some advantages. So the problem here is when just breaking out of the variable and immediately inserting the payload is in the function test. So whenever we want to get the JavaScript executed, we somehow need to make the application execute this function, right? And we don't know if this ever happens without extensive user interaction. So we are going for this exploitation technique. So we are always trying to break out of all the JavaScript that is inside the eval call to have the alert executed immediately when the eval triggers. And this is quite complicated. So this is an example again. So we are visiting with this website, and in the usual case, so our taint engine picks up a flow because there's this call to eval, and we will see the complete string that went into eval in the legitimate case. And our taint engine will say, well, this is the user input. We will see it will start with the variable declaration. And what we do in this case is we parse this string with a JavaScript parser. And the parser will give us an abstract syntax tree of this JavaScript code. And this is the abstract syntax tree, so it says, okay, this is a function declaration, you're declaring a new function, then there is a function constructor, and then there is a block, these are these 2 guys. Then there is a declaration with an identifier called x, so we have this variable, and we see the string literal, which is our UL, which is the user input. And this is basically the injection point. And what we are trying to do with this AST is we are trying to traverse this upwards. So we have the injection point, which is here, which we know that this is the injection point because the taint engine told us. And then we're just doing the following. we are in a string literal, so we need to get out of it, right? How to end a string literal? Insert a quote. After the quote, we're going up to the next parent element, because it's a tree, and we say, well, this is a declaration, right? So a declaration ends with a semicolon, so we insert a semicolon. Afterwards, we see, well, there is a block, and we close the block by inserting a parenthesis. And for function constructor and function declaration, we do not insert anything. We just say, okay, these are opaque values, and we have our breakout sequence that we need to generate the JavaScript exploit. With this breakout sequence, we also choose the comment sequence, which is a simple JavaScript comment, and we can generate the exploit. So with the breakout sequence, we put some arbitrary code that we want to execute, and we put the comment sequence, and it's ready. And then we insert the payload into the URL, and if you execute this is the resulting code. So we see the function test is being evaled, it has a variable declaration, and then our payload starts, breaks out of the function, and in the eval we see the alert, and we will see an alert window popping up. Okay, so that's it. I think this was a bit difficult and very complex. So we used this system to validate the flows. So we now had the 24 million flows, and we wanted to generate exploits for them. So, but before we did that, we cleaned up the flows a bit. So we had 24 or 25 million flows, and we said we only want flows that are directly executable with JavaScript and HTML. So we, for example, left out injections into URLs because they are pretty hard to exploit. So this left us with about 4 million flows that directly went into document write, into eval, into inner HTML, and so on. And then we said we only want flows that we directly control. So we had a lot of exploits where we can indirectly influence the behavior of the exploit. We said let's go for the easy things, just where we really control the value as an attacker, which left us with 1.8 million flows. And then we said, well, visiting 1.8 million URLs is still a bit a lot. We don't only have 6 computers, so we need to clean up a bit more. So we said we will disregard everything that is encoded. So encoding is often wrong, but we said when we see some form of encoding, we just say, it's probably fine, get rid of this thing. We don't look at it for now, we look at it later. And we will see something in the future work section. And this left us with 300,000 data flows that were unencoded, where we control the source, and where the thing directly executes HTML or JavaScript. And for these 300,000 flows, we generated exploits with our exploit generation techniques. And this ended up in 180,000 unique test cases. So why 180,000? We generated 300,000 exploits. Then we built URLs for that. But often we had the same URL for different vulnerabilities, right? You have a document write, you have 3 document writes in the same page, and they all write a very similar code. It all results in the same exploit. So from the 300,000, we got 180,000 unique exploits. And well, we triggered that, or we crawled all these 180,000 URLs. And from these 180,000 URLs, we got about 70,000 that triggered XSSs. So we roughly found 70,000, but it's not real 70,000, because often you have that one JavaScript library, and that is contained in every page of the web page. Or you have a blog post that is vulnerable, and you have 500 blog posts in the blog. Then you have 500 exploits that work, but it's only one vulnerability in the code. So we tried to have some uniqueness criterion. So we checked where exactly the function was. So for example, we used line numbers and column numbers to determine if this is the same exploit. And using our uniqueness criterion, we found 8,000 unique vulnerabilities in about 700 domains. But these 700 domains were not necessarily in our data set. So we wanted to crawl the Alexa top 5,000. But the Alexa top 5,000 often have frames pointing to other websites, to advertisers. And we were not interested in the advertisers and in all the other web pages. So we cleaned that as well. And we were left with 6,000 unique exploits on roughly 480% of the Alexa top 500 websites, which is about 9.6% of all the websites that we scanned. And this percentage is only a lower bound of the vulnerabilities. So we did not do any authentication to the website. So if you crawl Facebook without authentication, it's basically the login page. We did not follow anything else than the first link on the page, right? We didn't follow links on the second page. We also didn't crawl resources that were included. For example, as a script that has a MIME type of text HTML or so, we didn't crawl that. So maybe there are more vulnerabilities, but it's at least 9.6%. Okay, so let me quickly summarize before we come to the exciting part, the demos. And yeah, what did we do? So we created a tool to detect data flows in web applications, and we mounted this tool onto a crawler and found a lot of data flows. And we also built an exploit generator to exploit these data flows automatically. And with that, we were able to cross-site script 480 pages of the Alexa top 5,000 web pages. And if you're interested in the details, there's also a paper that you can check. And I have a quick link here. I guess you can get it from the slides later on, or from the video, or write it down now. Okay, so that was the part, official part with camera. And now I have some future work and follow-up and demo stuff if you're interested.